Hello students, welcome back. Lesson 14 is a continuation of Lesson 13. Let us continue over to Section 3, Inferences about the difference of the means for two independent samples. Previously in Section 1, we went through this case. The two-sample inference for two completely dependent samples, both of which originated from a single sample from a single population. Like this example. We have two samples, pre-class sample and post-class sample, but these two samples are completely dependent, and they're all paired up with respect to these subjects. So for example, subject number 1, this pair of data, subject number 2, this pair of data, and so on. Therefore, we can simply subtract one from the other, and we end up with a single sample. So we end up with a one-sample inference problem. And this is a case for two completely dependent samples. Now, what if we have two independent samples? And they may be coming from two different populations, or maybe coming from two different samples of same population, or even they may come from the same sample, as a matter of fact. I mean, let's go back to this example. Let's imagine this case. We have this pre-class numbers and post-class numbers, but somebody lost track of the subjects. So we have these numbers, but nobody knows which number belongs to which person. In that case, we lose these kind of pairings, so we cannot simply take the differences. In that case, what do? We have to consider these as two independent samples, and then work out the new method that we are going to apply. In short, this method we are going to study here right now, the two-sample inferences for two independent samples. This case is more general. I mean, this case is the technique that can be applied in more general situation. And of course, even more general will be correlated data, but that's not something we are going to be doing here at this moment. Okay, how do we do it actually? Three things to remember. Number one, the mean. Well, that's simple. Take the difference. After all, we are talking about difference of means. So there you go. Subtract one from the other. That's number one. Number two, standard error. Here's the standard error formula, and it's Pythagorean. Hypotenuse squared is horizontal squared plus vertical squared, and then taking the square root, we get the hypotenuse. And what is SE1 and what is SE2? Well, remember the formula, S over square root of n. So putting S over square root of n into this, S over square root of n into this, and doing your computation, you're going to get the final expression. But I don't think that's very useful. And this Pythagorean is going to be better. And of course, SE being S over square root of n, you should know that's formula number 2, titled number 2. All right. That's number 1, and that's number 2, and here's number 3, the degree of freedom. For one sample inference, the degree of freedom was no big deal. All we had was just n-1. But for two sample inference, now we're getting into two-dimensional case, at least partially. Things are more complicated. And as you can see, we have this complicated formula which develops into something this complicated, oh my goodness. But it turns out you don't really have to worry about something this complicated. This is sufficient. Let me expand the font so that you can read better. Look at the numerator. You have SE to the 4th power, but SE, you just calculated it. So taking the 4th power, we get the numerator. Now look at the denominator. Denominator consists of sum of two fractions, but look at the numerators of each. we have SC1 to the fourth power, SC2 to the fourth power, and we must have calculated these two. So you can put those in and you can do your computation. And as for the degree of freedom, n-1 for this, n-1 for that, not too bad at all. So if you do it this way, it looks really, really bad. But if you look at it this way, it doesn't look too bad. You'll see what I mean. All right, here we go. The heights of 20 randomly selected women and 30 randomly selected men were independently obtained from the student body of a certain college. And we have this data table. We are talking about men and women and two different sample sizes, so we cannot pair the data and subtract. What do? Well, we have to do these. And the first step is to get the difference of means. And that's easy, taking the difference of means. And I can even do it in my mental math. It's 6.0 because, yeah, it's easy. Now, as for standard error, you need the first standard error and the second standard error. And can you do that? You need S over square root of n and S over square root of n. Yes, you can do all those. There you go. Taking the difference, you get the center, expected value of the difference. Now, as for the standard error, one for men and one for women, S over square root of n, S over square root of n, all right? And then use Pythagorean, and you get the standard error for the entire inference problem. So you're going to be using this and this SC associated to this visualization, centered at 6.0 and 95% in the middle. And then you have to add the margin of error and subtract the margin of error. So center plus t times SC, center minus t times SC. That's how things work, remember? And which SC? Well, there you go. You just calculate it. And which t-score? That's a good question. You have to do the degree of freedom. Remember? You did this. That was easy. And you did this. Okay. All right. And then went through a picture briefly. Now, number 3. Let's find out the degree of freedom. You need the degree of freedom in order to look up the t-score from your t-table. How do you find out your degree of freedom? Well, let me just tell you the best method. That's the formula, isn't it? And let me expand the font. That's the formula, SC to the fourth power. And you just calculate its SC. This one to the fourth power. That goes to the numerator. All right. And look at the denominator. You have sum of two fractions, but their numerators are SC1 to the fourth power, SC2 to the fourth power. And as for SC1 and SC2, well, we calculated one for men and one for women. And then fourth power, okay, this to the fourth power, that to the fourth power. Don't ask me why we end up with fourth power. It's beyond what we are going to do here. And then finally, degrees of freedom. For men, 30 minus 1, so that's 29. For women, 20 minus 1, so that's 19. And we're complete. We completed this expression. From this point on, it's just a calculator work, and if you do it right, you're going to get 37.2, about 37. And that's the degree of freedom that you're going to be using. So look up the t-table and do your estimation accordingly. And that could be a bit of a problem because if you look at the t-table, you see, you want this 25%, 2.5%, excuse me, which corresponds to 95%. Look at the degree of freedom. We have 30 and then jump over to 40. So how do you deal with 37? Well, you can either estimate somewhere in between, or you can just go to a bit of a safe side and then just take smaller degree of freedom or larger t-value for bigger margin of error, 2.042, you can go ahead and do that. Or you can do appropriate estimation somewhere in between. I mean 2.042 versus 2.021, about 2.03 or something like that. You can do that too. I wouldn't mind either way. But of course, by far the best way to handle it is to use statistical calculator as I did here. So if I actually do that, then I end up with 2.02619 based upon the degree of freedom of 37. As a matter of fact, I can do even better. Instead of this 37, I could have used this decimal as a matter of fact. And 2.0258, that would have been even better than this one actually. This kind of computation was, of course, too complicated when these theories were developed in early 1920s, I think, 1930s, 1920s, I think. But nowadays, this kind of computation is not much of a deal. So you don't really have to force yourself into integer value by appropriate rounding on this degree of freedom. As I just showed you before, today's statistical calculation tools can handle decimal expression of degree of freedom with no trouble whatsoever. But here I used integer value and got up to here as a t-score, and you can calculate your endpoint like this: center minus margin of error t times SE, center plus the margin of error t times SE, which will result in, oops, too big, this expression of the confidence interval. Here is mathematical computation. By the way, there's another method from the textbook. This method is definitely better, but there's another method. I don't like it and it's not very good, but I will tolerate it because in the textbook. Simply take the smaller degree of freedom. You see, this formula here, oh my, that's too complicated, so let's not worry about it. Simply take the smaller of the two, and small sample size is 20, so 20 minus 1, 19. Just go with 19. In this t-table, go with a degree of freedom of 19. And then what do you get? You get 2.093? Yeah. 2.093. So 2.093. And then use that as your t-score. And then center minus standard error, t times SE, center plus t times SE, so that you end up with this expression of the confidence interval. I will tolerate it. It's not very good because, the smaller the degree of freedom, the more spread out the t-curve, and consequently, the bigger the confidence interval and the bigger the margin of error. So after all this interval estimation is not very good. Now, if you use this method, then you get higher degree of freedom. So this t-curve is closer to the z-curve, which is more concentrated toward the center. So you get smaller margin of error and smaller confidence interval. So the estimation is that much better. So use this method whenever possible, even though I will tolerate the solution because it's in the textbook. If I give an exam problem like this, then I will accept the textbook solution. But if I give you a homework problem or project problem, which come with that degree of freedom formula, then you'll have to use that.